Okay, good morning. So, last class we started to talk about, or we actually talked about overfitting, fitting, and normal fitting. And further, we went on and then we took those algorithms from scikit-learn and we applied it on the Titanic dataset. Okay, and what we saw was basic application of those algorithms. We did not play too much with fine tuning at that point. And today, actually, I want to focus on what is fine tuning and how do we arrange those things, or how do we find the best option. Okay. So before going ahead, do you have any questions? Okay. Okay. So in that case, let me go ahead and um, yes, let me go ahead and we'll talk about fine tuning. And the whole idea of fine tuning is to be able to get the best hyperparameters. Okay, so these terms parameters and hyperparameters, I've been talking about this like on and off, but maybe not with a formal explanation of sorts. And today maybe we can discuss a little bit upon what are parameters and what are hyperparameters and how do we separate the two. Okay, so here I've drawn two circles, model parameters and hyperparameters. And we can see that though both are variables that can hold value, their purposes and their meanings are different. Okay. So for this example, let's say this. Do you know what kind of model this is? Have you ever come across this equation, especially in context?
Weighted sum?
Yes, excellent. That's a weighted sum. And specifically in context of data science, this represents a perceptron. This represents like the most basic unit of a neural network. Okay. This also represents something that you would see when we do something called as linear regression. Okay. So the output is equal to the sum of all the different inputs. So xij are inputs multiplied by w, and w are weights. So here weights goes from 0, w0, w1, w2, wm, so on. Okay. So the parameters for this model are these weights w0, w1, w2, w3, wm, and so on. Okay. Xij are inputs, m is the number of dimensions that we have, and yi is the output that we have. And these terms look like model parameters. Okay, or these terms are parameters that we would want to learn from the data. Now, in contrast to that, we see these kind of variables, which are called as hyperparameters. Something like what are the number of iterations we should have, what should be the test size, what is the random state, how deep do you want the neural network to be, or if you're looking at neighbors, how many neighbors do we have, what is alpha and what are these components, how many folds, what is a penalty, do we have a penalty, do we have cross validation, and so on. So these are also decisions that we take regarding the model. But if you have to differentiate, maybe we can say that these are at a lower level. That is, these are the parameters that represent the model, and these are the hyperparameters that we use to train the model, or we use to process the model. So I've got few terms here for parameters and hyperparameters. Maybe we can go through them. So parameters are required by model when predicting. So once we have trained the model, we will use actually these parameters to try and predict what is going to happen next. Or when we get unseen data, we will be using these parameters to predict the answer. Whereas hyperparameters, we use that to estimate model parameters. Okay, required by processes to estimate model parameters. So when we are trying to learn these parameters, okay, then we may use these points. But once our model is trained, we don't generally have dependence on on hyperparameters, but we depend upon model parameters and to predict for unseen cases. Additionally, these model parameters, they are learned from the data. So we use your data, whatever rows and columns and features that we have, we will use that data to generally learn what these values are. Okay, whereas these values, they are specified by the practitioner. So we as a data scientist, we will choose what values to keep for these so that our model learns well, or our model is able to understand well. Okay, so this is generally specified by a practitioner. Now, whatever I'm saying, just hold on to it. This is not 100% right. I'm just getting some general guidelines. Okay. Finally, generally they are not set manually. So you would not want to set these guys manually, especially for machine learning, because maybe you can try setting manually for a few values here and there when your data is less. But when your data increases above a certain point and you have high dimensional data, we actually cannot do this manually. There is no chance that we would want to do this manually as well. So this happens automatically from the model. Whereas for these guys, you may use some heuristics, or you may use some past experience, or you may use some idea that you learn in the process. Okay, here also we do things automatically, but when we try to do things automatically, the idea is different. We are not doing it from the data here. We are doing it from experience, or we're trying to do it from heuristics and things like that. Okay, and these data are saved as part of the learned model, and they are considered as part of the learned model. Whereas for all of these guys, we'll be tuning them for given task. Okay, so it's not that one iteration will be good for all or so on. Depending upon the task at hand, we would want to tune these different values and then control them. So hopefully I'm clear in explaining what are parameters and what are hyperparameters. To give an example, maybe for the value of k, the value of neighbors, it comes as a parameter, but distance would be, value of neighbors would come as a hyperparameter, whereas distance would come as the parameter, model of the parameter. Or if you're doing naive Bayes, let's say decision trees, when you're doing decision trees, then uh, which features will be used first to divide the tree, and then how will that tree be created would be part of your model parameters. Whereas decisions like what kind of measurement that I will use for finding out chaos, that is, if I'll use entropy or if I'll use Gini score, or how much depth I want for the tree, or how many uh, uh, after how many pure nodes I would want to stop, and things like that. So those decisions will be part of your hyperparameters. Okay. Is this clear? Do you have any questions on this? Okay, so let me go ahead. So the idea is we have to, the training of the model to a very large extent depends upon the values of these hyperparameters. Okay, so they depend on, okay, I was also talking about one more thing, that whatever I'm saying, you have to consider this half correct. The reason for that is, especially when we try to go towards deep learning, when we try to go to somewhere towards deep learning, the idea of deep learning is that we want to learn these hyperparameters as well. Deep learning, these hyperparameters are also something that we would want to learn from the data. So we are not even trying for hyperparameters with deep learning. The problem becomes so complex that only huge amounts of data can save us. Okay? So that is probably the only exception to this rule. But for the most part, we would want to specify the hyperparameters as a practitioner. Okay. Going ahead, if then we want to do fine tuning, as I also said, fine tuning is very important because they control to a very good extent how good your model will be. Okay. So when we are doing fine tuning, we would want to try multiple options for multiple features. Okay. So let's say an algorithm like random forest regressor. Okay, it has features like What are the number of estimators you want? What are the max features you want? Or do you want bootstrapping or not? And these are decisions, these are questions that we would want to answer for applying this algorithm. Like this, different algorithms may have different number of features, and those different number of features can take several options. So if you start taking different options, very quickly this number will become out of hand, and to do it manually will be quite complex. Okay, so scikit-learn provides a method to us called as grid search, and this grid search is a very interesting function because it allows us to create multiple options for different features, and it will uh, run or train the model for all of those options, and it will give us our scoring and things like that. Okay, so in this case we are trying to use an algorithm called as random forest regressor. So this is a regression algorithm, random forest, and this random forest can take multiple parameters. Okay, so first what we do is we call from scikit-learn model selection, we import a function called as grid search CV. Okay, grid search CV stands for cross validation. Okay, and we define a parameter grid. A parameter grid is what are the options that we want our model to try. Okay. So here, can you tell me what is the data type of this param grid?
Dictionary.
No. See where it starts, param grid, and where it ends.
Okay, inside it is
So inside this dictionary, what is this one?
uh,
Yes, that's a list, right? So
but
param grid.
how inside list why there is a dictionary then?
So the dictionary are the elements of that list.
Okay.
So in Python, there is no strict rule that your elements needs to be integers or strings or anything. You can have any kind of object as your elements of the dictionary of the list. So param grid here is a list, and to that list we are providing two dictionaries as elements. Now this you rightly said is a dictionary. This dictionary has two key value pairs. So the key is n estimators. The value here is a list of three elements, and the key here, the next key is max features. The value here is a list of elements, and then we have another dictionary with these key value, and key value. Okay, so these are the different things that we want to try out for this model. So what we have to do is first we have to check out for this model what are the different features that are available, what kind of values they can take. Okay, once you figure that out, you see what values you want to play with, because this classifier or this model, this algorithm may have several such estimators. Okay, several such features, and we would want to choose which features we want to play with. You put those in the key value pairs in dictionary. And can you tell me how many combinations we have for this model? Okay, let's look at the first dictionary. For this first dictionary, how many combinations are there?
3 crores, 4 crores. There's a lot of combinations.
Yeah, just for the first one.
3 into 4.
Yeah, for this dictionary, we have 12 options to try. The 12 options will be one option here and then three or four options here. So with n estimators as 3, we'll try for max features as 2, 4, 6, 8. For n estimators as 10, we will try 2, 4, 6, 8. And then with 30, we'll try 2, 4, 6, 8. So that gives us 12 categories here. So 12 options or 12 combinations will come from the first dictionary. The second dictionary, can you tell me how many combinations will be there?
6 combination.
So we'll have 6 combinations from the second dictionary. And the total number of combinations will be the addition of these two ways, which is 12 plus 6 is equal to 18. So we have 18 combinations defined by this parameter grid. So if you look at the second dictionary, we have a feature, we have a hyperparameter called as bootstrap is equal to false. The first case, we don't have it. in the first case, the default value of Bootstrap is true. So that is why even if you don't mention here, so when we try to put these features, this may have lot of hyperparameters which may already have a default value. So by setting things up here, we just say, okay, what other values you want apart from default values, and so on. Okay. So here we have 18 test cases that we want to run. We will load our model. Again, this will somewhere up, we have to define from scikit-learn.trees or scikit-learn.ensemble import random forest regressor. So we create an instance of this model into forest regressor. We call grid search CV. So grid search CV takes parameters like this. We will first pass what is the classifier or what is the regressor that you want to train. So we'll put, okay, the name of the model. Param grid is this variable, which will give us the options that you want to try for these guys. CV, can you bring what CV is?
Cross validation is
Excellent. So when we say cross validation is equal to 5, what does that mean?
5 set.
Yes. So we'll take the training set, divide it into 5 parts, and for each part we will have one fold of training, one iteration of training, where this part will be our validation, everything else will be our training. So when you are running one combination, you will have to run this. You have to train this model 5 times. That is what CV is equal to 5 stands for. And a scoring is negative mean squared error. So this is a one metric used for regressors. So it's a very commonly used metric. So they have used this metric. Okay. So calling grid search creates this variable grid search, which is an object of type grid search. So this can be used as your algorithm. Like for forest regressor, what you would do is forest regressor.fit. Similarly, we can use grid search.fit. But this grid search, along with our model, it also has our parameters and all our combinations that we set up here. So we take this object, grid search, we do dot fit with whatever is our data. So our data would be your X values and your Y values. Okay. So your independent variables or predictor variables along with your Y value, which is your target variable or response variable and so on. So once you run for these algorithms, grid search will systematically go through all of these 18 models. And for each of these 18 models, it has to run it 5 times. So it will have 50 times, 80 times or 90. So it will run 90 models. And out of those 90 models, it will use this scoring to identify which one gave us the best results. Okay. So once the model is run, your grid search has a lot of information in it. So when I do grid search dot best parameters, I can see the output gives us this much. So here, basically what it says, after going through all of these combinations, it found that max features of 6 and number of estimators is equal to 30 gave the best results. Does that make sense? Okay. Additionally, we can find out multiple things along with best parameters. So best parameters tells you what are the best combinations, and once you have the best combinations, then you would have to again define your model, and you would have to apply these parameters and then get the best model. Okay. But you could do also one thing, grid search dot best estimator stores the best model itself. Okay. So your grid search at best estimator will be a random forest regressor object, which has all the default options, bootstrap criteria, blah, blah. And these options that you have learned. So max features is equal to 6 and n estimators is equal to 30 is additionally what it will have. Along with all the other default options, it will put these also, and it will return to you the stored classifier. So you can just load these grid search.best estimator into a different object and then train the model with that directly. Additionally, it also gives us your intermediate results. So here it made 18 models. For each of those 18 models, it gives us what are the scores and so on. Okay, what was the score? So here, what we do is we take grid search. Those results are available in CV results. So here we have taken CV results, cross validation results, copied that into another variable, and we have just executed a for loop to see what all options are there. So here we are writing for, okay. So CV results is a CV res is a dictionary, and that dictionary will have multiple key value pairs. So some key value pairs are what is the mean test score and what is the params. Okay. So what in this case what we are doing is we are taking these two values, mean test scores and CV params, and we are zipping these two values. So zipping these two values in terms of Python, what it means is you are making you're getting it ready for this for loop implementation, where it will combine these two values into a tuple, and once you take a tuple in the for loop, you can extract the tuple into variables. So you can directly get mean score and params here. So mean score and params will be uh, the different instances of this dictionary and this dictionary. Okay. So you get that value in mean score and params, and then you print what is the mean score and what is the params, which gives us these values. So here it gives us an idea of which feature gave what score, and so on. You can get some more understanding about your model. Okay. One more idea of doing this. One more idea of doing this is that we would one more option is, so we saw during our algorithms, we saw the difference between decision trees and random forests, and the key idea of decision tree and random forest was that random forest is wisdom of the crowd, that we can take multiple models and merge them together, and what output they give will be better than the output of the individual crowd. So similarly here what we can do is, once we have your CV results, you can take the top 5 or top 4 models that worked very nicely, okay, and then instead of just having one model, create an ensemble out of these 4 or 5 models, and for that ensemble you can use that ensemble as your final model to give out your answer. So these things can be done with fine tuning and grid search. Similar to grid search, there is one more kind of search called as randomized search. Okay. And the difference between the two is grid search will so if you have less number of options, that is, if you have less number of options, you can try for all possible combinations and so on, and it will finish fairly fast. But let's say you have hundreds and thousands of different combinations, then training or going through one such search will take a long amount of time. Okay. In those cases, we can use something called as random search, where random search says that we'll put almost like we have too many options. So either we have too less iterations with very small number of values, or we have so many different uh, hyperparameters that you want to play around with. And if you have too many of these guys, in randomized search, what can happen is you can define, just one second. For randomized search, you can define how many iterations you want to go, and randomly from this entire space, it will take those many iterations. So let's say I want to try for 100,000 iterations, so it will go through those 1,000 iterations randomly within the space that we have given, and within that space, it will say for 1,000 iterations, this was the best result that it got. Okay, so here, if this is especially important uh, when your cost is fixed. So let's say I remember I don't know, Anand may also recall that we were working on some training some models, and it would take so long. So what we would do is we would generally in the office Friday night is we will write all automation code, we will run the code and we leave it, and by the time we come on Monday morning, we have the results ready. Or many of the times, even after coming Monday morning, I would see that it will take another few hours or so for the model to train. So this is taking like more than 48, 50 hours and so on. So when you're doing a normal grid search, you don't have an option of stopping in between and so on. But with random search, what you can do is you can see how long one iteration takes. Uh, calculate the cost, how much time do you have, and let's say you're going for lunch, which is a 1 hour break, and you say within that 1 hour you want to train some models so that your PC is not occupied. You calculate that how many iterations will be taken, start your training, and then just leave for lunch. By the time you come back in 1 hour, your scores will be ready and so on. So all those things can be done with random search. The usage is very similar to how we did for grid search. Okay, we will call uh, param grid and so on. Just that we'll have an additional feature saying 1000 iterations or 10 iterations, as long, like depending on how long each iteration takes and how much time you have. You can set that value, and then it will randomly search within that space and give the best results from that values. Okay. Do you have any questions? Okay. So in that case, let me shift to the computer. We'll try to implement for the Titanic dataset. Uh, how would grid search change our answers? Okay. So here, interestingly, I did not get time to do it first and then discuss the results. So my hope is that when we try to do it now, it will not give too much problems and it will work fine. So I'll just execute these lines till we reach preprocessed data and so on. I'll just keep on executing these cells. Okay, so far no problem. We have reached modeling. I'll cross all of these guys. Okay, and maybe before testing, we will start a section and we'll name that section engineering. Let me call this 7. Maybe testing, we can put it as 8. Okay, so so far we have seen these algorithms or with our normal fitting cross validation of tenfold. We trained with KNN, giving us a best score of 82.94, decision tree 79, random forest 80.47, naive bayes 77.88, and support vector machines as 83.28. So from this we took SVM, but let us now try using grid search to see can we improve some of these accuracies. Okay, the first thing we will import grid search. So from sklearn dot model selection, import grid search. Okay. We will also define okay, one more thing that we did not do. Let me also see train is the name of our dataset. Okay, I do train.head. Train.describe. Okay, not so bad. Okay, then fine. So there was one step we call as feature scaling, which is required especially when your data is quite separate. In the sense, your ranges are very different. Then we do also a process called as feature scaling. Here, probably it is not required. All the data is very close. We are between 0 and 4, which is uh, which is fine. Feature scaling may not be required at this point. Let us let us take algorithms. Let's say our first algorithm is KNN. We would want to train for KNN. So first we'll find out for KNN what are the parameters that we can play. So KNN is not there. Ah. So the name given by scikit-learn is K neighbors classifier. So we'll do what is the help for K neighbors classifier. And when we check the help, we can play around with neighbors. Default value of neighbors is 5. I think in our case, we had given neighbors of 13 values. Okay. The default value is 5. Uh, Along with neighbors, weights can be either uniform or distance. Default is uniform. And okay. Your algorithm can be auto, ball tree, KD tree, brute. Leaf size can be default as 30. P power blah blah. Metric str will default as Minkowski. This metric is used for the tree. The default metric is Minkowski with p is equal to 2 is equivalent for okay. This is for Euclidean distance and so on. So metric here. Okay. I'm just trying to see in general what are the different things we can control. Yeah. So far these things. So let me make a list. So we'll define something called as param grid. Now, in the example that I showed in the slide, we used a list of dictionaries because there was some option that I wanted to use separately. So for true or false, for true we want to do something else. For bootstrapping is equal to true, we want to do something else. And for bootstrapping is equal to false, we want to do something else. That is why we had a list of dictionaries. Normally, we could just settle with one dictionary, and these values should be fine. And if let's say we'll come across a case where we don't want to try, then we will create a list of dictionaries. Okay. So for now, let's take n neighbors. So I'll take n neighbors, and n neighbors can take different values. So we will take a range. Let's say we'll go from 5 neighbors to 25 neighbors, and we'll take gaps of 1 itself, so we don't need to specify it. So we are trying all these options. Maybe let's even go for 30 neighbors. Let's go ahead. Weights can take multiple options. I'll take weights. It can be uniform or distance. So we'll try both these sides. Then we have algorithm. Let's try these also. Ball tree, KD tree, and brute. Auto is a different algorithm. It will attempt to decide the most appropriate based on the values passed through the method fit. So one of these 3 it will die. So I don't need to give auto as an option. Okay. Leaf size is passed to ball tree or K tree. This can affect the speed of the construction plan. So we'll not play with this. Let that be. So this parameter decides P decides what is the distance metric we'll use. Okay. Here it is saying when P is equal to 1, this is equivalent to using Manhattan distance. When 2, it is for Euclidean distance. For arbitrary P, Minkowski distance is used. So let's keep P as 1, 2, and 3. So we'll go for all options. So we are trying Manhattan, we are trying Euclidean, and maybe one more extra. And yeah, Njobs we will not define, we'll define it for the model directly. So these are the several options that we want to try. Let's try to estimate how many cases, or let's leave it this because I know when running grid search, it tells us what is the total number of sets that we are trying to learn. Now we will take K neighbors. So let's say KNN is our K neighbors classifier. and we'll call our grid search is equal to grid search CV. We pass the model, we pass parameter as the options. We'll give one more thing as verbose. So verbose is how much do you want to print? Okay, so let me see what is the default value. Verbose 0, so it will not print anything, but I can see what verbose 1 or 2 will do. Let's go down. The higher the more messages. So excellent help result. Let me put 2 and let me put Njobs is equal to -1. So Njobs is basically the number of parallel tasks that you want to be running. Uh, so here, depending, so if I just put 1, it will use 1 core to run these parallel jobs. When I put -1, it will check for my system what is the number of cores, and based on that decide automatically uh, how many it can use. So I think normally when I use njob is equal to -1, it takes 8 cores, which is the size of my number of cores in my system. Along with that, we have to say CV. So let me put cross validation is equal to. So in the earlier cases, we had used k-fold. So we'll use the same k-fold. K-fold comes with 10 splits. So that's fine. So we'll say cross validation is managed by k-fold. And scoring. So we'll use accuracy as used earlier. With these options, I think we are good to go to run the model. So we have defined grid search. Now we'll do a grid search dot fit to train the model. What is the data that I provide? So I'll go with train data and target. So my x-axis is in train data. My y value is target. Yeah, I guess we are ready. Let me go ahead and execute this. Steering Njobs. Is it n_jobs? Let me do search. Let's see features. Yeah, n_jobs. We will change that. Okay. Oh, so there are 450 different candidates in these combinations, and with CV is equal to 10, it has to train 4,500 different times, of which KNN is maybe for this less data, it is not that complex. It has already finished 2,240. Okay, now within 27 seconds, it finished all these combinations. And after all these combinations, this is the combination that gave us the best results. Okay, so let us explore this a little bit more. So we can go to grid search. Grid search itself will have a lot of data, and we want to see what is the best parameters. So I see best, and I do a tab. These are the best parameters. So it says algorithm brute was the best, neighbors 10 was the best, P1, that is Manhattan distance, worked better than Euclidean, and weights uniform. Okay. Right. Do you find this interesting? I am actually quite impressed by what grid search can do, because very quickly we went through all of these combinations and it has thrown to us something interesting. Let us see what results and so on. We'll also see what is the best estimator, which we can directly load and then train. So it has copied these instructions into the best estimator, which is fine. We wanted to see results. So let's say grid search dot CV results. So grid search dot CV results is a dictionary which has mean fit time, standard fit time. Okay, let me take that into CRS is equal to this, and we want to say, let me do CV results dot keys. So these are the things that is stored within the model. We have mean fit time, standard fit time, mean score time, standard score time, parameter algorithms, weights, and so on. Okay. So times I'm not so much interested in. What I'm more interested in is, okay, what is test score? So these are the test. Okay, we have mean test score and we have params. So let us, we printed for the case in the PPT. Let's print here also and see what options we have. So we have it in CV results. Let us go back here and say for mean score and params in zip of CV results. We go for means test score, CV result, params. So this will print.
What will this zip will do?
Yeah, I'll tell you. Mean score params. So if you just look at this guy, this will be a list. Let me run this. This will be a list of all the different scores. Okay. And similarly, if we look at this params, this will be again a list of all these combinations. When you do a zip of these two guys, it will take both this list and convert that into a tuple. Yeah, very good. If I do print of this, okay. Let me do list of zip of this. So this is what it will convert. It will take the first value of mean test score. It will take the first value of this, join those together as a tuple. And then the combination will result into a list. So the first tuple will be first value of this, first value of this. Next one will be second value of this, second value of this, and so on. So the advantage is when we do it that way and give it to mean, it can directly unzip or it can directly, what do you say, tuple unpack here and use it here. Otherwise, if I have to run through two lists, what I have to do is I have to define a counter. I will say let I is equal to index is equal to 0, and I'll say for, okay, you understood what I have to do, right?
Yes, I think I got it.
Yeah, I have to run a loop for this variable and then use CVRES mean score I index and CVRES
Yeah.
params index. So
But why can't we append in y-axis or something?
append in y-axis means?
Instead of creating two tuples, we can just join as another list or something, right? Why you went for the tuple itself?
So the interesting thing with tuple is this unpacking you can do only with tuple. You cannot
Oh,
do this unpacking with lists or anything else.
okay,
So
okay.
only when you have a list of tuples, you can do this unpacking. And yeah,
Yeah, I think it's clear.
for that reason. So it's just a bit neater. I don't have to do that extra step of defining that iterator and then mess with it. Here we can directly play with it. Okay. So this is our combination. Let us execute this. Balance. Okay. So it gives us an idea what is happening here. Let me go to the starting. Sorry. So with 5 neighbors and Manhattan, it gave us 81. 5 neighbors and what has changed in this one? Okay, distance. Okay, weight went from uniform to distance. Much. you can see there are different scores that we are getting. So around 8. So even on a worst day, we are doing around 79, 80%, which is good. If I go ahead, do we have some great numbers? 82.9. Okay. 83. So for 22 neighbors, Manhattan and so on. Anyways, our best combination was 10 neighbors and 1. Do I have it here? 10 neighbors. Okay, 10 neighbors and 1, somewhere around here. Let us look at our best score. Our best score is 83.6. Okay, so this is what we did. I think which is fairly good. In our base implementation with KNN, we had gone 82.94 and SVM had given 83.28. With the search, we have got 83.6, which is better than all the results we got so far. So maybe we can skip this part. Let's say now we have our model, we have our best estimator. The next task would be to uh, get the model and train it there. So let me take our classifier is equal to with search.best estimator and clf.fit for train data and target. And once we have fit it, we will want to okay. So here we would not know our score. Will we know our score? Let me do this fit and clf dot. Do we have score? Yes. Okay, excellent. Cannot read this. Score. We have to give x and y. So let's train. Okay, for train data itself, tell what is the score. 83.9. Okay. So even with this, we get for the training accuracy, we get 83.9 percentage accuracy as our best accuracy that we can get from KNN. Okay, have you gotten this?
Yeah.
Okay, maybe we can try for one more algorithm. So this we did for KNN. Maybe now I can just copy all these things together and say the next one. Let's try for decision tree. So first thing would be, let me do help of decision tree. We'll see what things we can play around. We can play with criteria. Let's do that. Can be Gini or entropy. Splitter can be best or random. Let's do that. Max depth none, so expanded until all leaves are pure. We can keep some depth and see. Let's put a range from 5 to 25 with gaps of 5. And along with that, we'll put none as well as an option. Max sample split. Let me not mess with these guys. Let's say max features. skip that. So the thing is, depending upon how much we know about the algorithm, we can go as much detail and define things. Let me try only for these options. It will be decision tree classifier. We call it DT. Everything else we keep same. Fit we keep same. Let's execute this. So just 80 fits. It has found this code. We'll find out what is the grid search dot test params. Any max plan to test. I think it took all the default options. And just estimator. Let's directly train the model. We'll say decision tree estimator. This is our best estimator. And we'll do dt.fit for train data and target. And we'll do a dt.score of train data target. Great. So this gives us 90%. You see, just by running this search, we may be trying different options, which may actually increase our accuracy. So here we were getting, we had no one close to 90%. We had 83.2, which is the best we had gotten. And just by playing around with these hyperparameters, we can get higher results. Okay. Does that make sense? I would also want to try one more thing. Instead of grid search CV, I want to try random search CV. Let's do that. Randomized search CV. So let's take this guy's only and copy it. And instead of grid search, we'll call randomized. Sorry. I didn't execute this. And let's see what parameters we can call for this one. So estimator param distributions, which is okay, it's not called param grid, param distributions. Number of iterations, I think this is the value that we can change. Scoring remains same, CV remains same, verbose and jobs. So everything is fine. I think this will become param distributions is equal to param grid, and we will define number of iterations. So we know all these combinations come to 1000 values, 4500 values. Let's say we want to limit it to 1000 iterations. So if I do 1000 and execute, it is still going for, okay, let us see what it does. So and it is something else. What is this? The total space of parameters 450 is smaller than number of iterations. This. So we have to talk about this number, the number of candidates, rather than this number. So let's take these numbers. We'll go for just 100. So it will say 10 folds for 100 candidates, 1000 fits, and after 1000, hopefully it stops. Okay. And within this, what it has got as best, let us find out. Okay. Search best params. It has found weights uniform. Okay. So among the 100 candidates that it tried, it got 26 neighbors as the best answer. And what was the score? 82.5. Okay, not that bad. I hope you have understood both these cases, right? Randomized search CV and grid search CV. Great. Okay. In that case, we can stop now. What I would, what I would expect or want from you guys is, now we have seen one example of from start to end. We have seen one full example. So Titanic dataset, starting from data pre-processing and all those exploration, visualization, to creating a model, even fine-tuning a model and testing a model, we have done. So now you can actually go on to kaggle.com and you can create an account and start attempting problems. So Titanic here we have solved, but you may want to get some answers, predictions, and upload your submission on Titanic and see what results you get. Also, I talked about one more data set that I was looking into. I think I shared on the WhatsApp chat regarding hard data set. So let me see if I can find that. Okay, just 1 second. Where do I get mine? Accomplishments. Okay. Yes. You may actually try this one. So this is a fairly simple data. It's not very complicated, and the data has 13 attributes, train, test. It is also a categorical classification problem for hard data set. You can go through this material, look at this data, download this data, and try to upload the results for this one also. Maybe in next class uh, I can discuss something on the heart disease prediction, just to get you guys started, and then you can take some time and work on this problem, even on the Titanic problem. Now, once you know the theory, the next thing that remains is just practice. You have to practice on multiple data sets so that you can get a feel of how things work out. And Kaggle is an excellent place for doing that. Okay. Anand, you want to say something?
No, 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 no.
Okay. Okay, then we will stop for today. Thank you. Bye bye.
Okay, then bye.